Welcome everyone to today's PCS seminar. It's a great pleasure to have with us today Professor Rudolf Roemer. And I would like to invite our scientific host, Alexei, to introduce our today's speaker. Please, Alexei.
Yeah, thanks, Dylan. So we're having today Professor Rudolf Roemer from University of Warwick talking about localization properties in disordered 2- and 3-dimensional Lieb lattices and their extensions. So Professor Roemer received his PhD at the University of Utah in 1994, where he was working with Bill Sutherland, and he was then holding a number of positions in Indian Institute of Science in Bangalore, in Aachen, and he was for a long time at the Technical University in Chemnitz. And since 2002, he's at University of Warwick in the UK, first as a lecturer, then associate professor, and since 2010 as a full professor. Since 2016, he's also holding a visiting professorship at the Shanghai University in China. So as you can infer partially from the talk, his interests are centered around disordered interacting quantum systems, including Anderson localization, random matrices, and metal insulator transitions, as well as the more computational aspects. So how to attack these systems computationally. And so with this, Professor Roemer, the screen is all yours. So let's welcome the speaker.
Thank you very much, Alexei, for this very kind introduction. Thanks to all of you for wanting to listen to me and coming in. And thanks, of course, to the Institute in Daejeon for actually inviting me. So today I'd like to talk about some work that we recently did together with colleagues from Shanghai University, namely master student Xiaoyu Mao, PhD student Jie Liu, and my long-term colleague and friend Xianxin Song. And introduction, you already sort of heard that I spent some time in Chemnitz, and actually Xianxin Song and myself, we were both postdocs in Chemnitz many years back. And that's where the connection comes from. And you actually see everyone, and you probably figure out who are the older and who are the younger people from just the pictures on the screen. So today I'd like to tell you a little bit about some of the recent work we did in sort of this area of flat bands, but really it's one of the areas of research that I managed to avoid for many, many years, and it's quite surprising that I actually avoided them so consistently. And the surprise is the following. Alexei already told you that I studied for a PhD with Bill Sutherland at the University of Utah at the time. And it is actually Bill Sutherland who in many ways invented the whole game of flat band physics. Namely, flat bands are, as I've written up here, periodic media with at least one completely dispersionless Bloch band. And that's what Bill Sutherland discovered when he looked at localization of electronic wave functions in special lattices. And if I'm not entirely mistaken, he was motivated to do this by looking at so-called quasi-periodic systems, which, as I'm sure you probably all know, in the mid-1980s had just been discovered and were sort of very interesting for many people to study. But even before I did my PhD at the early 1990s, I should have known a little bit about flat bands, because in my diploma thesis at the university in Berlin, I actually worked on a paper by Lieb. And Lieb, in a physical review letter from 1989, had proposed two theorems on the Hubbard model. And in the second theorem, he looked and proposed, he gave an actual proof of the existence of large degeneracy for special topology in a certain Hubbard model. And that was in many ways one of the first proofs of a macroscopic magnetic state in these low-dimensional systems. That was a two-dimensional system he looked at. And the second theorem that he had, he also proved a certain uniqueness of the ground state in such systems. And I actually spent my diploma thesis on trying to generalize this theorem one, and again, avoiding totally that there's actually this underlying Lieb lattice that gave rise to this large magnetic degeneracy in that particular topology. Now, starting on from these early works, then lots of additional work has been done, and the names that really should be mentioned here are Mielke, Tasaki, and Komoto. Komoto, for example, was a collaborator with Bill in the late 1980s on those quasiperiodic systems. That's sort of where the connection is there. And I'm sure you're well aware that actually you at your institute have sort of some of the leading groups in that area, at least on the theoretical side. And Sergei and his people, Alexei is on here as well as our host. And then also Daniel Laikam sort of are some of the really leading experts in the field. They've written a number of very nice review articles. So in many ways, I'm here a beginner giving a talk in front of the experts, which I hope go lightly with me. Following on from these early theoretical works, it took a while for the experiments in many which way to catch up. And catch up, however, then they did, and doing it by going to a system that at the time when these original works had been devised didn't even exist. Namely, they went to photonic systems. And here I should mention at least two works by Seba Mukherjee, and the second paper by Seba Mukherjee. And I mention Seba in particular because Seba actually visited us in early 2018. And because we had just done work on Aronoff-Kasher caging, which is very similar, of course, to so-called Aronoff-Bohm caging, which also happens in these flat band systems. And what Seba had done is that they had, in photonic lattices, they had basically made those special lattices which exhibit flat band states. And one of these special lattices you can, for example, see here. I'm trying to sort of draw it in red. So you see this is a quasi one-dimensional lattice with sites at certain positions. Sorry for this red spike that just appeared. And in the third dimension in here is just the way they grow those photonic lattices. That has really not much to do with the lattice that we're really looking at. So we're looking at a lattice that is basically sort of a diamond connection of lattices. Okay, I'm not very good in drawing, but you see sort of the diamond lattice that is emerging here. And then you can see that at certain frequencies in the system or energies, of course, equivalently, you see that what you're getting is either a state where you have light intensity all throughout the system, or we have light intensity at very compactly localized sites, of course, corresponding to these compactly localized states. So these are what I will, through the rest of the talk, call so-called flat band states, and these are not flat band states. So a double cross across FB is supposed to indicate these are not flat band states. And that is basically a quasi 1D system. So again, there's the spike appearing when I draw with my little mouse. So in this quasi 1D system, you can have these flat band states, these quasi-localized, these compactly localized states, but you can also have it in a 2D system. And this 2D system here is what's called a Lieb lattice. We'll see a picture in a second. And again, in this Lieb lattice, you can have, which is really a two-dimensional lattice, you can have compactly localized states, but you can also have non-compactly localized states, which here you can see even a little bit better, are really spread out through the system. So we now have theoretical papers that tell us there should be so-called compactly localized states in these flat bands. And we have a couple of experiments that tell us this should also exist. But that still didn't get me started even thinking about all this. And it was not until sort of in 2018, we met at the 11th International Workshop on Disordered Systems at your place in Dijon, where I met all the major players in the field. Namely, here's Daniel, and there's Sergei, and there's the whole conference down here. And of course, we listened to quite a number of talks on these flat band systems. And I just told you that Seba had visited us earlier in 2018. So we got a little bit interested and thought, well, maybe there's something that we can do about it. And that's then when I learned that actually sort of the Lieb lattices I should have known already from my very old work. Diploma work is now probably 30 years ago, yes. So the models that we then decided to study are Lieb models, but also extended Lieb models. So the original Lieb model is basically this two-dimensional, no, sorry, okay, not that guy. The original Lieb model is this two-dimensional lattice. You see the normal two-dimensional lattice is just a normal two-dimensional square lattice given by these blue sides. And of course, the unit cell is here given by this light blue side. And the first Lieb lattice is when you, in addition to these blue sides, put sort of some interstitial sides, which are indicated here by red, between the blue sides. And then the unit cell actually corresponds of these three lightly colored sides. And clearly you can now think about extending that. Instead of putting just one little red dot between the blue dots, you can also put two red dots between the blue dots, or you can carry on, you put three sides between the blue dots, or you can carry on even further and put four. And I think you see how that can be generalized. Furthermore, you can also do it in 3D. So here we have the normal three-dimensional cubic lattice system. And again, you put red dots between the blue sides. You get sort of the first Lieb lattice, and that's the normal Lieb lattice in 3 dimensions. And when I say normal, of course, Lieb himself looked at the 2-dimensional situation, whereas this is already in 3-dimensional, it's an extension now. And then you see you can put 2 red sides between the blues, you can put 3, you can put 4, you can think of basically a whole family of these Lieb lattices and their extensions in 2 as well as in 3D. And what I find interesting about these lattices is that they are so very simple to construct. They start from a normal cubic system, and then you go to these other sort of cubic systems, but you retain most of the cubic symmetry, which makes some of the sort of methods that you like to use, and here we're going to use mostly numerics, makes it much easier to implement. When you think back to some of the complicated photonic lattices that were studied early on, these quasi-1D systems, the diamond lattice, for example, is a bit more tricky to build up. Okay, and then you can actually look at these compactly localized states, and a simple example for the Lieb lattice, which is well known, is when you have states which are -1 at one side, 0 at the blue sides, +1 at the other side, 0 at the blue side, -1 at the side as you go around, and then again +1 as you go around like this. So this is one of those compactly localized states that you can have on those Lieb lattices. So let's study those. And of course, when we started doing this in 2018, we thought we were the first to do it, but very quickly learned that that's not the case. Namely, some other people had already looked at clean extended Lieb lattices in 2D. And I've given the citation down here, as you can see. And so when you look at these lattices, you can, for example, just look at their dispersion curves. And that's what I've given over here. And you see, for example, that a 2-dimensional Lieb lattice with one red ball interspaced, so the normal Lieb lattice has 3 dispersion curves, namely a top one and a bottom one. They meet at a sort of direct light point, but in between, at a particular energy equal to 0, you have your flat band. There's your flat band in here. And then for the Lieb lattice with 2 red balls, 2 extra sides, then here you're having 5 bands, where 3 bands are actually dispersive bands. So this is a dispersive band, there's a dispersive band here, there's a dispersive band here, but in between you have 2 flat bands. And this is sort of simple, simple dispersive band construction in those tight binding Hamiltonians. You can solve those actually exactly the formulas, which we've done in the paper, but which was also already done before in that paper down here. And you see, you have a proliferation of dispersive and of flat bands, actually. So you can see that L2 of n exhibits n flat bands and n+1 dispersive bands. Okay, so I think that's a good test case for flat band physics. Let's look at it in 3D, similar. So when you look at the models here, of course, in 3D, it is more tricky to actually draw the dispersion relations. In 2D, you can see the dispersion relations as a function of k gives you, of course, a surface. In 3D, that gives you then, well, sort of a 3-dimensional situation. It's very hard to draw. So what we've just drawn is what people do in solid state physics. So you draw it from certain k points. So the gamma point is, for example, the k equals 0, 0, 0 point. I'm trying to draw 3 zeros here. And
Professor Roemer,
yeah.
Sorry to interrupt you. We have a question from Alexei.
Yes, please.
Yeah, thanks. I mean, for some reason, I cannot raise the hand. So my question is, I think for the 3D, you have more possible stackings. I think if you, I mean, did you consider those? I think if you take a 2D Lieb lattice, the usual one, you can simply place, so to say, another Lieb lattice on top and go on forever. But I think you can also shift it by half a lattice spacing, and you would still get a structure that has a flat band.
So you're saying, I'll try to draw it here. You take one Lieb lattice in 2D with these extra sides in between, and then you can put another Lieb lattice in 2D under it.
Yeah.
Right? Like this. And you could just have a simple connection between them.
Yes.
Or you could put another guy across it. Then you were, of course, then you're basically back to this. Yes, I agree. You can make combinations of those, right? So you could, for example, you could think of, here I have 2 extra sides on the rim. I could, whereas here I also have 2 extra sides, but I could, in this direction and the vertical direction, I could only put 1 extra side in between like this. So you can probably do something as complicated as LD, and then you can have an NX and an NY.
Yeah, right. But that's not exactly what I meant. What I meant is that you take a 2D Lieb lattice, so you place the next layer, but I think you have a choice. I mean, you can shift it by half lattice spacing, say in X direction.
Oh, even more complicated. Yes, you can probably do that. Yes.
And I think you can even actually end with a non-periodic structure that still has a huge degeneracy at 0 energy, because you can now, every time you add a layer, you can decide whether you want to shift by half lattice spacing or not.
Oh, that's not what I wanted.
I think what Alexei is saying is that instead of the cubic lattice, you could have started with the FCC or the BCC blue lattice and then dress it with the other sides.
Hi, Amnon. Yeah. Are you still in Korea?
No, I'm in Israel.
Oh, good Lord.
But hi, Rudy.
Well, there's many ways in which you can do it. We haven't done it. We went for the simplest case because it's already complicated enough, right?
Yes.
Yes, yes, you can do it. You have to tell me why it would be particularly interesting to do it. So from our point of view, the motivation basically comes in I think in sort of one more slide what we really want to do. So maybe I'll just skip ahead to this and tell you why we're interested in doing what we're doing.
Okay.
So generally, we are mostly interested in the 3D situation because you guys probably know I'm sort of someone who does a lot in 3D Anderson localization, and I'm interested to see what do these compactly localized states do, how do they change Anderson localization. And there hasn't been that much done in 3D, in sort of the flat band structure. Mostly what people have done in flat bands is sort of 1D, quasi 1D, and then the 2D situations. So of course, because before we do 3D, let's look at what is happening in 2D, and we have the similar sort of questions. Namely, does the presence of these compactly localized states lead to novel localization effects, maybe for those dispersive bands? So the normal 2-dimensional localization, do we somehow see that that we have these flat bands in our system? Do we see that? How does it change the localization? And the other point is, we have these compactly localized states, but they are, of course, degenerate in energy. So when I put in a little bit of disorder, I basically destroy a little bit this perfect degeneracy, but I could still think that I can now make with a finite number of states due to the superposition, I can still form a very large state. because normally sort of in this localization game, you have this intuitive picture that a large density of states leads to a large localization lengths. But these are compactly localized states. So what is going on? They should be most localized, but they have a high DOS. Can it sort of lead to a large localization lengths? Is there something that could be interesting to look at? And I admit it's a very sort of naive picture. And those of you who have thought about it already know the answer. But when we started, we hadn't really thought about it. We were just thinking, okay, let's have a look at this in 2D. Similar in 3D, but in 3D, of course, we have a complication or more excitement. Namely, we have a metal insulator transition. So we were thinking, what happens to this transition, in particular, what happens to the energy disorder phase diagram? What happens to the critical disorder strengths when we have these additional localized states in our system? You know, and we'll see it in a few seconds, that in 3 dimensions where we have this Anderson localization, for weak disorder, we have a sea of extended states. And now in the sea of extended states, there should be these compactly localized states living in there. So what does that mean for the sea of extended states that I also have at certain energies, these localized states? What happens to these special localized states, right? So Alexei, does it sort of answer your question? We're not that interested in many ways in understanding how particular forms of Lieb lattices work. This is something which I think is more interested in people that try to do quantum engineering with these clean Lieb lattices, that try to find particular effects, let's say, try to, at certain energies, have flat band states. We're more interested in destroying the flat band states by disorder and looking at how do they survive. It's a different sort of perspective.
Okay.
So here, exactly this is what I just said. How do we destroy them? Namely, could there be that there's a region of localized states around the flat band energies for small disorders that somehow survive? Because we know at no disorder, we want to have these compactly localized states. We know at weak disorder, everything should be extended in a normal Anderson model. What is happening to them? And last, of course, the ever-present question, does that somehow affect the critical properties of the MIT? So that's really where we're coming from, which is a slightly different motivation from, I think, what people have that look at these compactly localized states and the flat bands in these systems for their own sake. So, okay, let's start simply. Namely, let's look at not what happens in the clean systems, but within disordered systems. Let's first look at the density of states. So we know, if we go back, from the dispersion relations, for example, in 2 dimensions, we see that for L to 1, we have flat band state at energy 0. For L to 2, we have flat band states at energy plus and minus 1. For L3, we now have flat band energies at 0 again, at sort of some number in between, which we can actually compute. It's something like square root of 3/2. And we also know what the energies are for the other guys, where they all are sort of here. Now let's look what happens to these states when we include a bit of disorder. And here now I'm showing you for all these systems. So this guy connects down here, this guy connects down here, this one down here. I hope this is all clear. You see the density of states. So for L to 1, the original flat band energy was at 0. This is what survives this peak when you start to include a bit of disorder. Yes, we have here smoothed the density of states, because these are just exact diagonalization results for relatively small system sizes, averaged for different disorder configuration. So we did a bit of Gaussian smoothing just to see what happens to the density of states. You see the initial peak that we get in the density of states due to the highly degenerate compactly localized states very quickly dies out, and at about disorder 2 is basically most of the knowledge of there ever having been degenerate states have vanished. And by 4, so when you get to the size of roughly the band, you basically have vanished. The whole thing has vanished overall. And this is the fate that happens to all the flat band energies. So for L22, there was it at -1 and +1. And this is exactly the flat band sort of degeneracies that you see here. And again, they die out very quickly. By the way, these extra sort of semi-maxima that you see, they are not actually degeneracies, these are the normal dispersive bands. So these are the normal density states for one of them, sort of, let's say, cosine bands. So this is the same here. So this is basically not a flat band state. This is just the normal dispersive band, which also has a maximum there before you broaden it by the disorder. So then for L33, you see the 3 flat bands here, they die out. And for L34, you see the 4 flat bands here, they also die out relatively quickly. So you would expect by the time you hit W2, well, everything should have vanished. Now, this is a bit of bad information, because in 2D,
Question?
you know, yeah, go on.
Does disorder 2 correspond to a mixing of the dispersive curve with flat bands, in a sense? The distance between the flat band and the dispersive band, how does that compare to this critical W equals 2?
Well, I wouldn't call it critical W. So look at
I know it's a crossover.
I mean, not in the universal critical sense, but just look at how these bands look like. You see, for example, for L21, you see the bandwidth is for this guy is roughly 3. For the top dispersive band, for the bottom dispersive band is also 3. So by the time you get to 2, it is clear that you've basically the bands are totally mixed now, right? Yeah. So it's not surprising that this happens. But
right, so I wonder if at larger N, there is a larger gap between the flat band and the neighboring dispersive curve, but the transition still happens at this order roughly equals to 2. So
it's the larger you make your N, like the L24, yeah, the flatter all the bands basically become. You just fill this sort of, look at the region, it still is so -3 to +3 over here.
Yeah.
Right? So overall, even the dispersive bands become flatter and flatter here.
But that doesn't influence the crossover from the large density of states to a small density of states.
Well, when you look here,
in fact, for N equals 4, it seems to happen even below 2.
Exactly. If you were to draw a line sort of here, you say, well, actually, you could argue that here in this model, you have to go all the way to 4 before the difference in the density of states has totally washed out. He would say, well, probably at this point, it has already washed out, which happens at 3.
Right. Mm-hmm.
Right. So there's these 2 effects. In many ways, you can sort of understand this already, what is really happening here, because what is effectively happening in one of those legs between the blue sides? You put in more and more red sides, and the red sides are effectively just a one-dimensional chain, right? So basically the transport between the blue sides, if you increase that parameter here, that becomes more and more one-dimensional.
The randomness is only on the blue sides or on every side?
No, the randomness is on all the sides.
It's everywhere, okay.
In this simple case, it's everywhere.
Mm-hmm.
Right, so basically what you have, if you increase this parameter here, you become more and more one-dimensional.
Yeah.
And that's roughly what you see in these systems. Okay, now what we're actually, of course, really interested, oh, sorry, I haven't talked about this. So this is the 3D situation. It looks very similar to the 2D situation, to the 3D situation. Again, we look at the density of states. The bandwidth is a bit larger in 3D, of course, and hence it takes a little bit longer. So you wouldn't say at 2, the difference is washed out, but the difference is washed out basically by the time you reach 4. And we have the same effect as before if we go straight away here. So here it happens a little bit earlier already. Okay. So now let's look at transport. In order for us to do transport, we want to look at the scaling of the localization lengths. We want to use the transfer matrix method. And I'm sure many of you will be familiar with this, but I'll highlight it here anyhow. So I highlight and explain how we do the transfer matrix method here, because it is instructive to see what actually changes when you include the extra Lieb sites. So in the normal Schrödinger equation, you would write your Schrödinger equation as such that the hopping terms into the z+1 direction, which you could call something like the future, are given by the psi at the present and the psi values at the past. And they are being connected by basically the hopping amplitudes. And if you have a one-dimensional system, then t is just a number. But if you have 2 or 3-dimensional system, then t really is a matrix. And instead of just dividing by it, you should have to take the inverse of that matrix. And now the red sides that I have in these 3-dimensional or in the 2-dimensional system, the red sides effectively lead to a real normalization of the simple Schrödinger equation, such that in these red expressions for the on-site energies and for the hopping terms, I now need to include these red sides, and they need to a renormalization of the on-site energy and the renormalization of the hopping terms. But otherwise, the structure of the transfer matrix remains the same, because the underlying topology of my system is still square or cubic. And then I can rewrite the Schrödinger equation in this sort of transfer matrix equation. There is a closing parenthesis missing. And again, I think many of you are familiar with this transfer matrix equation. It basically tells me if I want to know what happens in the future, I need to know what happened in the past, and then I can successfully go through my system, and I can go through my system such that in the z direction which I've chosen for the propagation, I make that larger and larger and larger. And normally you say you set a certain convergence criteria, and later we'll see results, for example, for 1% or for 0.1% of a convergence criteria. And then also, this all depends on the system width, and the system width from now on, I shall denote by 1/m. And what we're going to study is we're going to look at the largest localization lengths that I get by doing the transfer matrix as a function of the system size m. And that really is defined basically something like that. It is a multiplication of the transfer matrix from the first side to the final z side. This is supposedly a capital Z. Yeah, so this is the transfer matrix for a certain position set. And then I do the same just with transposed. So this little matrix, this product of matrices capital T is what I call little tau here. I take, I diagonalize the matrix that comes out. I take the 1/2 the power m root, and probably I forgot a log somewhere in between. And here I'm getting then finally my localization length. Yeah, I forgot a log, sorry. So this is standard transfer matrix. Now, how does it look like in our systems? And you see that I have just given you the simplest example, namely L21 and L31. And in L21, I told you that the epsilon has to be renormalized. So if I go back, this is my renormalized epsilon here. And that's how it really looks like in the simplest case. And these are the positions of the red, the sort of the Lieb sides or the rim sides. And you see that they get renormalized into an effective on-site energy. Similar, the hopping terms, which is this guy here. Now they also get renormalized. And again, by sort of the on-site energy that I have at the red sides, they get renormalized. And that effectively what I do is when I talk about transfer matrix, I go back from the Lieb lattice that I have here, and I make transfer matrix in a normal square lattice with these renormalized parameters, the renormalized on-site energy and the renormalized hopping that I have here. And in L31 in 3D, I can do exactly the same. And here, for example, just the renormalized on-site energy becomes complicated quite a bit, and that's for the simplest case. So I hope you can appreciate what happens if instead of L31, I would take L34, which we've also done. You see how complicated sort of this renormalization term will be. And when Alexei proposed that we could take other lattices, he's certainly right, but it gets ever more complicated. So, you know, we were quite happy to have just done these sides here. And by the way, this is, of course, the renormalized hopping term that I'm having. And again, you see that's quite complicated. Okay, is everyone sort of relatively happy with the transfer matrix method? Because I think from now on, I'm only going to talk about us having localization lengths, which we compute from the transfer matrix and doing something with them. Is everyone happy? Any questions? No, then I'll carry on. Okay, next ingredient we want, particularly if we want to go to 3D, but not only for 3D, is we want to look at finite size scaling, and the quantity there we're looking at is this so-called reduced localization length, capital lambda m, which is just the localization length that we just spoke about, obtained from transfer matrix divided by the system width. When we do that, we have a dimensionless quantity, and with this dimensionless quantity, we can do proper scaling. And the scaling idea is that lambda m depends via a scaling function only on m divided by psi, and psi is a scaling parameter, and the scaling parameter itself depends on the energy and the disorder where I'm looking at the system. So the lambda m's don't depend on energy and disorder and m separately. They only depend on the system size and energy disorder in this particular form that I've given here to the top left. This is again something that people have been using, this single parameter scaling in Anderson localization for many years. I'm not going to talk about sort of the motivation behind that, but it's important for us to note that if we estimate the scaling parameter, it is effectively the localization length for the infinite system. Once we obtain it from finite size scaling, we can get an approximation of what the infinite localization length should look like. So what happens, and these are standard results from normal Anderson, you plot your capital lambda as a function of m for different m's and as a function of disorder, and you see that there is a systematic behavior. On one side, the guys go down, on the other side, the guys go up as a function of system size, and I probably just did exactly the opposite. I think it should go up to the left and should go down to the right as a function of system size. Why going to the right? Well, if you are in a perfectly localized situation, which you will be at large disorder, so somewhere at large disorder, your localization length should become independent of system size, because you're localized much smaller than your system size. It's independent. So if you divide it by capital M to get sort of the capital lambda out, then the larger you make your m, this thing should then just go down. And you see also on the right-hand side, as I've drawn here, it goes down, whereas on the left-hand side, it goes up. And somewhere in between, there's a crossing point, well developed or with a bit of a shift, and that's when you have your transition. So you would say somewhere here, there should be a transition. And once you have all the data and you plot it differently, you plotted the log of this lambda as a log of the scaling parameter, you see that your data all collapses onto two curves, namely a curve that goes down as you increase your system size, and that would be a curve that corresponds to an insulator, because it's exactly the same situation that we just talked about here. I make something bigger and bigger, and it becomes smaller, this lambda over m. But on the other hand, if I'm on the left-hand side of the transition, if I increase my system size, I go up, because in the metal, the state should be as big as the system size. If I make it bigger, it also grows. So, and in between, at a certain disorder, you have a metal insulator transition, which doesn't change with the system size. So it's system size independent, which is exactly the hallmark of the transition. And if you plot your scaling parameter, which I'm doing in this inset as a function of disorder, you'll see diverges. So again, for most of you, this is pretty standard, but you see these are the expectations that we should be having. So we're expecting that we see scaling curves if we have proper scaling in these Lieb lattices with disorder, and we expect to see two branches if I have a metal insulator transition, and one branch only, for example, a downward branch if I only have an insulating situation. So having done that, here are the results, what happens in 2D for our standard Lieb model, L to 1, so the normal Lieb lattice. We increase the disorders from 1 to 10, and we see that we get a curve like this after scaling, or even before scaling, which is in the inset. These are curves for different disorders plotted as a function of 1 over m. And you see, basically, we always have a slope that goes negative. I'm drawing it a bit more than what you actually see in the inset. So we have a curve which goes negative, which means that lambda over m becomes smaller as m becomes larger. We're plotting 1 over m, so large m is sort of to the left over here. And hence we are in a situation where we are localized. And if you then put all these curves together, you have the scaling curve that I have here. So we have this one branch, the one branch goes down, everything is localized. Everything is, it should be in 2 dimensions. We know in 2 dimensions, giving 1 parameter scaling, everything should be localized. Fine. So that is at the flat band energy of E equals 0 in the Lieb lattice. Nothing special about it. Or is it? Let's have a look. Well, the localization lengths in 2D should, I've said this before, if I go to large system size, become equal to the localization lengths in 2D for the infinite system. So this finite size scaling curve should become actually an identity. For large disorder, I want that f is basically nothing but 1, and hence that psi over m is the same as lambda over m, which means in these double logarithmic plots, I need something that has a slope 1. So let me just draw something slope 1, the point 0.1, 0.1, and the point 1, 1. You see here, I just draw a straight line, just PowerPoint in between. And you see that this curve really, if I make this stronger, the localization, the disorder stronger or my system size larger, really seems to go to this behavior, but not too well. So let's look at the other cases, namely L22, where the flat band is not at energy equals 0. All these results I'm showing on this graph are for equals 0. So the flat band is not at energy 0. The flat band was at 1. I'm still showing you the energy 0 curve. Similarly for L24, the flat band was not at equal to 0. I'm showing you the energy 0 curve. And let's look at this guy over here. I've done exactly the same. I plotted a slope 1, and you see that fits perfectly. Whereas when I have the flat band energy here, or in this case, it doesn't fit so perfectly. So already you see whether I have localization in a dispersive band or flat band, there is something not quite as simple as in the normal Anderson localization situation. So I don't get this agreement with this line for the flat bands. The localization for flat band energies seems to be different than the localization when I don't have flat band energies. So from before.
Udo, I have a question. This L2 plot which you show in the top right corner. So this is for an energy which is not a flat band energy.
This is for energy 0.
Aha,
but that's not a flat band energy in this particular model.
Right. So what if you go to the flat band energy in that model and measure the localization lengths there? What will happen?
I don't think we've done that actually. I'd have to look it up. I don't think we've done that because it's not so simple, right? You can do it, of course, but
just change the energy. Okay.
Well, but you know, these calculations still take time.
Yeah. I understand that. Well, yeah. Thank you.
May I ask a different question, Rudy? You showed that to go from the normal square lattice to the Lieb lattice, all you need to do is renormalize the bond and the site energies. Is that mapping from the bond to from the square lattice to the decorated Lieb lattice? Is that transformation analytic?
Sorry, it's the opposite. We go from the Lieb lattice to the normal.
You go from the Lieb lattice to the square lattice, and you obtain an effective Hamiltonian for the square lattice, which has random site energies and random bond energies.
Yes.
And I'm asking if that transformation is analytic. If it is, then I might expect that the curves should be mappable on each other, the curves you just showed, by using that transformation. So in some sense, they are universally related to each other.
Okay, what do you mean by analytic? The calculations, of course.
I mean, if they are singular, then I don't know if I can just map the curves because the singularities might enter.
Okay, so you mean analytic in sense of differentiable and all this. Well, okay, so you see there is of course a slight problem here. Namely, if the onset energy is equal to the energy you're looking at, you're dividing by 0. Right? And that's a feature that is in this all the time. What we are doing is we're cutting this off. We're saying if this energy difference is less than 10 to the minus 15, then use 10 to the minus 15 and forget about this. And then we're checking that if we take another number, the localization results are independent of this, right? But if you're thinking in terms of an actually analytic and differentiable derivation, then it's not quite that.
Yeah, so I wonder if those special points indicate some problem in the finite size scaling or in whatever.
I don't think they indicate a problem in the finite size scaling. They will be a problem when you go back to the clean system. Because when you go back to the clean system, then epsilons are all zero, but the energies are also zero. So at your flat band states, then the mapping breaks down, basically.
Right.
Right.
So from your scaling curves that you showed, you could extract the divergence of psi as function of W, both in 2 and in 3 dimensions. And
Yes.
I wonder if that divergence looks the same for the normal square or cubic lattice and for your Lieb-like systems.
Very good. We'll get to this. First of all, remember, yes, these days we tend to think that in 2D everything can be done, but still, remember that in 2D, Anderson localization is still a bit of a problem because the localization lengths diverge exponentially. So the smallest disorder we use is up to disorder 1. When we want to do it for different energies, actually down to disorder 1, because it becomes more and more tricky to actually do things. You see, even here, we have that the reduced localization length is 3, which means that the localization length is 3 times as wide as our system. So we have already done a pretty good job to get it collapsed onto this lovely scaling curve in 2 dimensions.
Mm-hmm.
This is sort of, even that is already tricky. And you'll see if we now go to 3D, it will be even more tricky. So nevertheless, before we go on, let's just sort of stop and remember what we've done. So at the flat band energies, the localization lengths are smaller than for the dispersive bands. I should have pointed this out. This is what the arrows tell us. So when we are at the dispersive bands, look at our lovely localization lengths, reduced 20 times larger than our system size. Whereas at the flat band energies, which are supposed to be compactly localized states, you somehow see these guys are more compactly localized, right? There's much smaller there. So they are more localized. So you see the remnants of what compactly localized means, even at finite disorder, even when you have this mix of these dispersive bands, because the disorder 1 is still strong. Okay, so we see that. And the scaling behavior does not follow at the flat band energy the simple behavior that we would expect from normal Anderson localization. Again, it is more strongly localized. So, okay, now let's also look again at energy equals 0. And let's just look at energy equal to 0. Let's not do sort of any scaling. And let's just see how does this localization length that we've estimated now, that the one that Amnon was just talking about, how does that look like as a function of disorder? And does it have a different scaling behavior? And we know in 1D, and this stuff should have nothing to do with 1D, the scaling behavior should be basically a number divided by disorder squared. In 2D, it should be this much more complicated form, according to Kramer-McKinnon. And let's see what happens. So let's look at the flat band. I'm plotting on the double logarithmic plot, double logarithmic scale here. And you see, for the flat band energy, I actually get very, very good one-dimensional behavior. Similarly, for the flat band at L23, I get basically very, very good one-dimensional behavior. Whereas if I'm at the dispersive energies in 2D, I know I shouldn't get anything that sort of looks like 1D. And I see what I'm actually getting is more something that looks like this 2D curve here. So if I look at my scaling, it seems to be fit better, but doesn't fit that well. But nevertheless, this here is the 1D behavior, this blue line. And you see there are clear deviations, at least here where the data is, there are clear deviations from the 1D behavior. And you remember that I told you back intuitively already early on that you can basically think of these additional sites as giving rise to some sort of 1D behavior. And we think this is what is actually happening when you look at the scaling curves in 2D. You see you have effectively 1D behavior at these flat band guys. So what you see is must be something like this. Well, at least the scaling curves have the same dependence on the W, which is okay.
Rudolf,
quite interesting.
Rudolf, I'm lost here. Can you show it again? Yes. So, so what do you want to say? You still measure the localization lengths, the scaling for the 2D system?
So I'm from these graphs here.
Yeah.
Right. I can estimate what is the scaling parameter as a function of disorder. How much do I need to shift my curves to get these scaling guys? Yeah. In 3 dimensions, that would give me the divergence at a certain disorder. Here it just gives me how does the localization length look like as a function of disorder.
Right.
Right? So it's the estimated infinite size localization length.
Can you show again this slide, please? Yes. So what we see is L21, for instance. Let's take this L21 flat band. So this is the scaling of the localization lengths of the 2D flat band state, so to say, at the flat band energy with W.
Sorry, I just lost my mouse. Okay, that's back. So this is the scaling of the estimated. Jesus, I lost my mouse. Yeah, of the estimated infinite system size localization length as a function of disorder at energy E equals 0.
For the 2D L21 model.
For the L21 model, the normal Lieb model.
What you tell is, why do you compare that with the 1D scaling? What is the point of that? I didn't understand that then.
Look, only thing we're doing, we're plotting this as a function of W. We try to understand it. What could it be, right? We know in 2D the behavior is supposed to be something like that. We expect 2D behavior. Right? We're doing effectively a 2-dimensional model here. So maybe the normal Anderson 2-dimensional scaling, I mean, 2-dimensional behavior is fulfilled.
Wait. So in 2D, you would expect exponential growth at small w, as you said before. So
well, that's the exponential growth here, right?
Yes, but that's not what you show in this plot, right? Isn't it?
So in this plot, I'm just showing you the data, right? I'm not doing anything. I'm just showing you the data. And the data on the double logarithmic plot for low disorder is a straight line.
Right. So it's not exponential.
Yeah, it's not. But it's only a straight line at these flat band guys. So for L21 and the energies.
I understand.
But it's not a straight line for these guys.
Right.
Does it mean that if you're
my question is
on the 2 left curves, you have the energy equals 0 is at the flat band is at energy 0, right?
Yes.
So does that mean that when the energy is at a flat band, the problem reduces in some sense to a 1D problem?
No, I don't think so. So
I can't say that. I can't say that. The only thing I can say is
let me ask the following. Look, we did something very simple a couple of years ago. We took a 1D system, okay, with a flat band, and then we looked how the scaling of the localization lengths goes with W at the flat band energy. And the answer is the following. If you go away from the flat band energy, you see this 1 over W squared scaling as you showed there in the top left part of your slide. But if you go to the flat band energy, you'll find the Cochise scaling 1 over W. And we have some reasons explaining that the effective disorder at the flat band energy there in this 1D problem is Cochise-like. So is that something similar? Would you get a Cochise-like, would a Cochise disorder in 2D give you a 1 over W squared scaling? In a just, otherwise normal.
Sorry, what a Cochise disorder? What do you mean by Cochise disorder?
Well, which has distributions which fall off, if I remember correctly, is 1 over W, 1 over epsilon squared or something like that. So, yeah, with a divergent second moment. Cochise disorder. Well,
yeah, but we haven't done any Cochise disorder. We have a uniform disorder distribution.
Yeah, so I understand. My statement is the following. In 1D, you can basically argue that at the flat band energy, the original normal disorder produces a Cochise-like disorder with a divergence variance and a faster, a smaller localization length, which scales in a different way, say not as 1 over W squared, but as 1 over W. So what I'm now wondering is whether in 2D, say the normal disorder at a non-flat band energy will give you exponential growth, But if you go to the flat band energy, perhaps it, as you show here, it shows you power law growth, and that power law follows again maybe from a Cauchy, an effective Cauchy distribution. That is my question.
May I rephrase that question? When you do the renormalization that we discussed before, going from the Lieb lattice back to the square lattice, by that you get a different distribution of the randomness on the renormalized square lattice. And the question is, you could take the original distribution of the randomness with the width W, and then map that distribution onto the distribution of the new site energies on the effective square lattice. And Sergei is asking, what is this new distribution of the renormalized random energies? And he conjectures that that will be a Cauchy distribution.
Well,
of course, you could do that. We haven't done it.
You can easily do numerically just by repeating your renormalization of the energies and look at the distribution.
Of course you could, but so what Sergei did, he did a one-dimensional model.
Yeah.
Saw that the localization does not follow the normal 1/W squared that you expect in 1D. And he said this is because he has a different distribution of on-site energies. They're Cochise distributed. In many ways, we've done something similar. We take a two-dimensional system, we renormalize it. We find that our localization at the flat band energies does not correspond to the normal two-dimensional exponential. This bond, we find something that corresponds to something else, and that something else is suspiciously close to the 1/W squared.
Yes, but what my question, Rudolf, let me rephrase my question. That's more a question to you and the experts from localization theory, which is, so the Cauchy distribution, when was a long time ago used in 1D systems to explicitly derive the 1/W divergency for the localization links. My question then is, was anything similar or comparable done for a 2D system? Because then, because what I'm trying to say, this is maybe this 1/W squared is not because it's somehow related to 1D, but it's because it's related to Cauchy, to diverging variances of.
It could be. I don't know, Sergei. It could be, right? Now your basic is you're giving the right interpretation, as Amnon said. You could say, now we've done effectively a model in 2D which has a different disorder distribution, and hence it should have a different behavior of the two-dimensional localization lengths, and maybe that is a 1/W squared, not because it's 1D, but it's just because you have a different distribution. That could be. The only thing I'm saying is I find the 1/W squared behavior.
Okay.
Yeah, but
I naively took it to indicate that.
Exactly that. I mean, the universality class of localization in 2 dimensions depends on the distribution of the random variables. And there may be literature in which people investigated the influence of the distribution on the exponents in 2D, or maybe even in 3D.
It could be. The only thing I know is that in 3 dimensions, the old works by sort of Kramer McKinnon tell you if you take a long tail distribution, it doesn't change, for example, the criticality. It doesn't change the universality class.
What do you find? What do you find in 3D?
Well, let's carry on then.
Yes.
Right. So, but the main point here is that, again, flat band localization and not flat band localization can be different.
Mm-hmm.
So yes, everything stays localized as you expected in 2D, but the quantitative localization is different. Now let's go to 3D. So this is just, I don't know, how we're doing in time. It's a lovely discussion. I think I'm out of time and I have already done. So what are we going to do now?
No, we have enough time. There were many questions and discussions, so just please continue.
Okay, let me show you what happens in 3D. So again, a review, what happens in the normal situation, normal Anderson cubic 3D. I have again an MIT, it's the curve that I showed you before. I get extended states, I get localized states. I'm just showing you little pictures of those. I get the critical states, and I get divergence of my localization lengths now at a particular disorder, which I would call the critical disorder. This is not the normal Anderson model. This is sort of slightly different Anderson model. Hence, this is not the 16.5 I have here. It's a slightly different sort of picture. And my localization length is supposed to diverge with the critical exponent. Nu, by the way, if my drawing becomes even worse, then I ran out of battery. Now I have to use the mouse to draw with. So, and the phase diagram in 3D looks roughly something like that. The bend edges at -6 and +6 for the clean system. If I then increase my disorder, I know that I have my sea of extended states indicated by this orange line here, where I have my extended states in the center. Whereas outside, I'm starting to get an ever-growing sort of region where I have localized states, and at the critical disorder, WC, then I go, everything is localized, right? So this roughly, this is how the phase diagram looks like in 3D. Of course, it's a schematic picture here. So these are the phase diagrams now for our Lieb models. How have we done it? Well, we first computed localization lengths for small system sizes. We looked at when do these curves cross, and that gives us, for example, here, low estimates of as a function of energy and in this direction disorder where the crossings should be. And then at particular selected energies, for example, energy 0 here, energy 1 here, and also some energies out, sort of larger energies. Then we did high precision runs. So the first runs for the low precision estimation of where the phase diagrams were done with 1% accuracy, and finally the high precision runs were done with 0.1% accuracy, all the way to systems that were 20 by 20 in terms of cross section, and then many millions and billions long until we have reached convergence. The experts may know that reaching now 30 squared or larger in normal Anderson 3D is not a problem anymore, but for these systems, because of the renormalization, you're still restricted to relatively small system sizes. Nevertheless, what we see is, just like we have it in the normal Anderson model, mouse, where are you? Oh, there. We have the sea of extended states, and we also have the sea of extended states for L to 1 down here. So in the center, when everything is gray, we have sort of this extended states, and we go down in disorder all the way to 1, W1, because then we cannot do much more with these accuracies. We cannot do it for all the energies, but for energy equal to 0, in the inset, you see that we're also looking all the way down to 0.01, just looking at the reduced localization lengths. And we see basically that with a function of system size, all the way to energy 0.01, the reduced localization length still grows. So all the way to 0.01 in disorder, this is an extended state down here. So we have to very close to energy equal to 0 before we see these compactly localized states again. So these compactly localized states, all the way down to disorder 0.01, are not visible in terms of whether something is extended or not. All right, that's how the phase diagram looks like for L21. Then we have L32 and we have L34. Sorry, L33. I don't think we did L34 anymore. Interesting here to note is that we in L32, where we have 3 dispersive bands, you see the 3 dispersive bands now all have their own independent lobes or seas of extended states. And then the localized states are emerging. By the way, these triangles just tell us that these are the band edges which then merge. So these are basically band gaps that we have here in these triangles still. And here we looked at the state at E equal 1. So there's a flat band state at E equal 1. Again, we down to this order 0.01, wanting to see what happens to this compactly localized states as we approach them by disorder from the top. And we see that here we still have that if we increase sort of our sort of system size, it goes up, of course. And we see that we stay extended all the way again to 0.01. So basically, we see these sort of seas of extended states, and we see that the flat band states don't really have much influence into the presence of these extended states. In particular, this expectation, will there be a region of localized states around the flat band energies for small disorders, is something that we don't see. That's basically what these guys tell us. They are not here when we look at them, or they are less than 0.01. They are less than 0.01 than when they might be appearing, right? So the idea was we could have a sea of localized states down around the flat band energies, and we don't see any evidence for this. That's the first thing. And I hope you appreciate that these phase diagrams look quite funny, actually. Sort of disjoint phase diagrams, I sort of like that. Now, furthermore, let's do now scaling. Again, we do it at particular energies. This is done for the normal Lieb model. We've done it at the flat band energy. Oh, sorry, this is the normal Lieb model at the flat band energy. This is not zero. This is one, energy one. This is at different disorders and different disorder 6, basically corresponding to those three states here. These three guys, the special energy. So energy 0 here, energy 1 here, and then disorder 6 here and disorder 3 here. And we see at all these places, we get basically crossing, not very good crossing, but there's still a bit of crossing. So there's quite a bit of density of states effects involved, but we can construct scaling curves and we can look at the divergence of our localization lengths in all these situations. And if I look at, for example, L33, again, at the flat band energy equals 0, I can also do it. So we've done it for all those models. And finally, now we're doing finite size scaling, and we come up with critical properties, things like critical exponents. And you see, these are the numbers that we get out of this. And they all seem to be roughly consistent with 0.59, particularly within the accuracy that we're having. And we also can come up with things like critical disorder strengths. And you see, that's interesting. The critical disorder strengths goes down if I go from the 3.1 model to the 3.2 model to the 3.3 model. So the higher, basically the N in the Lieb 3.3 model, the more rim sites, the more of the red sites I put in, the less disorder I need before everything is localized. You could have seen that as well from those phase diagrams again. So you see that the critical disorder here, when everything localized, is about 8. Then for L32, it's about less than 6. And for L33, it's less than 5. So you see that the more red sites, the more sort of Lieb sites I put in, the less disorder I need to localize. Putting in more Lieb sites leads to more localization naturally anyhow. Okay, so we have done all this lovely stuff. Oh, by the way, I should tell this here. So then we're looking at how does the critical exponent look like at sort of the model on a roughly arbitrary scale. Just put them all in. And these, the green dashed is the current accepted value, sort of the Slevin-Otsuki value. And the gray one is sort of another estimate that people have done based on multifactorial analysis. And you see that our results roughly cluster around these things. Scale here is from 1.4 to 1.8. So within the accuracy of our calculation, we cannot say that anything is systematically deviating from the normal Anderson model. It just seems to be the same. That you have sort of some large, sort of relatively large deviations is well expected within the accuracy of the results. Which means, okay, for our Lieb models, at the flat band energies, again, the localization behavior can be different. The phase diagrams do not develop these regions of localized states, at least up to this order that we can check. Yes, the phase diagrams are changing, but the universal properties like exponent remains the same. The rim sites act as, I would say, additional 1D localizers, but I think Sergei has a slightly different opinion on this, which is probably more informed than mine. And we always find that the critical disorder for the Lieb models is less than the critical disorder in the Anderson model. And overall, there isn't anything that was really surprising in the bloody thing. It's a bit, I have to admit, a bit boring in that sense, sort of throwing more disorder in these Lieb models. Maybe we've, okay, I had expected maybe to see something more interesting. But the story is not over, if you don't kick me out because of time. I remember at this workshop, we also listened to a certain gentleman that some of you may remember, namely Carlo Daniele, who was also one of the people interested and involved in much of this work on flatband states. And it turned out when we submitted our paper to PRB, that was a three-dimensional paper, we got interesting comments back from the referee. And one of the comments was, maybe you should make special disorder, namely make a disorder at the hub sites only, at the blue sites disorder, and don't put disorder on the red sites. And hence you have these compactly localized states surviving. So after the paper was accepted, we thought this was very well done by the referee. We got back to PRB and we said, look, we're going to do this now. Maybe the referee wants to join us. Maybe you could get in touch with the referee and ask if he wants to lift his anonymity. And he did, and turned out it was Carlo, which was quite a surprise. And since then, for a couple of months now, we've been working with Carlo, looking at what happens when we have the special disorder. So the disorder is now only at the blue sites. I think Amnon was mentioned this already. And first results, and I'm only showing you those for the density of states in the 2D model. We have similar density of state than 3D model, and we have already first results for phase diagrams. They tell us a much more interesting story. Remember, I told you before, the density of states basically washes out at around W2 or at least W4. Now I'm looking at the density of states, energy, and again, disorder now going to the back. And you see that now the degeneracy survives all the way up to disorder 4 or larger. And similar, now the disorder survives in the L22 case. And now these compactly localized states survive. And already from our transfer matrix results for this, we find that the phase diagrams already tend to look very weird. So something less boring than the normal Lieb model seems to be emerging. However, what we basically do when we do this disorder that Carlo suggested means we put no disorder on the red sides, which means effectively we lowered the disorder. And these Lieb models were already hard to converge with the disorder when disorder was everywhere. And now with this particular disorder, it's even harder to converge. And hence it is numerically much trickier to get some results out. So we're heavily challenged here how to do it. But nevertheless, we think that's quite interesting, this compactly localized states preserving disorder. And maybe something quite funny could come out of this. And with this, I finally close. I thank you very much for your attention. And the results in the somewhat more boring situations are in those 3 papers, if anyone is interested. And of course, I'm happy to take further questions.
Thank you, Professor Roemer, for this wonderful talk. Let's thank our speaker first. Oops. Okay. It's a lonely clap, but still we appreciate this very nice talk. So please, questions.
May I ask a question, please?
Yes, sure.
Rudy, hi, this is Victor. I wanted to ask you about your argument about this effective one-dimensional behavior, because if you are looking at your L2N model, then your argument that increasing N should lead quicker to the one-dimensional behavior. But unfortunately, you have it already at L2-1. So the question is, if you can show that for N equal 2, 3, 4, you are even closer, then your argument perfectly works. I'm talking, yeah, before, yeah, exactly. Because here you already have this effective one-dimensional behavior already in the very first L2-1, yeah? Am I right?
Yes.
Yeah. But according to your argument, increasing the number of red knobs, you should be closer and closer to one dimension, yeah?
Well, so what is going to be the limit if you put in more and more of the red nodes? Let's look at the dispersion as well. So let's sort of look at this case, right? Suppose you put in more and more of the red guys, you see you get more and more bands, right? And the bands become flatter and flatter and flatter, right? That's what is basically happening. So fundamentally, in the end, you're going to have really long 1D chains coupled sparsely across your system. So the only thing I think is I feel that this 1D-ness for most of the transport should survive. That you see something from this 1D behavior, and it's not quite right. But I was sort of thinking, we know that in 1D everything is localized. We know we have a pure point spectrum, right? And you sort of see that even the dispersive bands here, they become more flat and flat. So somehow I think this is what survives of the 1D-ness. I agree with you that in terms of localization, if I look at the 2D results that I have here, that if I go now to L35, I would have to expect even more 1D behavior, and I would probably expect it to be better to weaker disorders, but probably already also better to larger disorders. And I don't know in which way it should grow faster.
Okay.
So I look, but the only thing I really want to say is I find it surprising that I get my W squared behavior here, which is something I normally expect in 1D. And of course I could now, and it's, I mean, what Sergey and what Amnon said is certainly correct. You can now say, effectively, you're renormalizing, you have a different disorder distribution, and it could be that this different disorder distribution leads rise to a different W squared behavior. And that could be W squared not because it has something to do with 1D, but because for some other reason, right? But at this point, I'm only aware of a 1 over W squared behavior from 1D. I'm not aware of a W squared behavior from any other particular disorder distribution. So I just throw this observation in the room saying, this is what I observe.
Okay.
I ask the same, maybe the same question in a different term. In the usual Anderson model, W is measured in units of the nearest neighbor hopping.
Same here.
So the real variable is not really W, it's W over T, where T is the tunneling between nearest neighbors. Now, as you add more points, as you increase N, then the one-dimensional localization enters, and therefore the nearest neighbor effective hopping becomes smaller and smaller because the wave function along a bond decays faster because of the one-dimensionality. So could you re-plot your diagrams taking that into account? And since T becomes smaller, then of course the localization will happen faster because the variable is W over T, not W.
Okay, so what you're saying is I could also, where's my mouse again? I could plot something like a W prime, and the W prime is given by basically the effective W strengths, which I have once I do this renormalization.
Yes.
Right?
Yes, and you will be moving in this effective 2D diagram to smaller T and therefore to smaller W.
Yeah, but that's basically the same argument that I'm making by saying these guys become 1D. Yes, I could quantify that by trying to plot what is the average sort of T that you get when you have that, right? But remember, it's only going to be an average T because all the red guys themselves also have a little epsilon, so it will be more a distribution, like what Sergey was saying.
No, so the question is really what happens to the distribution of the original Anderson model had randomness only in the site energies of the blue dots, say, on the square lattice. And what you are doing here is you are introducing randomness also on the bonds. For many years in the 70s, there were arguments on the nature of the Anderson transition when you put the randomness on the sites or you put it on the bonds. And I'm not sure where that discussion has converged to in the meantime.
But I think, okay, but I think we all agree that going from the left to the right here is effectively leading to stronger localization, right? And I'm saying because this is because effectively have more 1D transport between the blue sites. And you're now worried about, can I describe this qualitatively? That is true, but you can also have a different point of view. So I'll try to draw it in here. A different way to make a Lieb model is, of course, to make the same normal Anderson model and then cut out this additional site that I have in the center, right? That's also a way which I can cut out from a normal square lattice. And that tells me that I cut out some transport channels. And this cutting out the transport channels is also expected to lead to more localization, because we know the more transport channels I have, the more tendency towards extended states. Cutting out transport channels means I have more tendency towards localization. And in fact, the way I'm cutting them out, if you look at, again, if I were to draw them in here as well, I'm cutting them out that more one-dimensional transport is left over. That's where my sort of argument comes from, one-dimensional transport. You could also then say, if I look at the T elements that I had in here and the epsilon elements that I had in here at the sites which I cut out, and try to make a new distribution for these guys, of course, that distribution would also change.
Yeah.
Right. So there are two ways in which you can look at that, but both of these ways clearly agree, saying that if I put in more and more of these red rim sites, I should get to more and more localization, and that's what we're seeing.
Yeah. Let me suggest another way to approach this. You can take the problem with n red sites, and you could renormalize it by mapping it not on the square lattice, but on the n=1 site. Take the n sites and eliminate them in favor of a single site representing them. Then you map, and that you can do analytically exactly in your model, because it's one-dimensional. It's easy to replace n sites by one effective site. That will map the general n model onto the n=1 model, however, again, with new distributions because of that renormalization. And my point was that as n increases, the effective hopping of that n effective model will become smaller and smaller because of the normalization in one dimension.
So there are many ways in which one can understand that the red sites lead to more localization, yes.
Yeah, I'm trying to find analytic ways somehow.
Yeah. Okay, any other questions?
Good.
Yeah, let me add a bit more to this before you get too tired, Udo. So thanks for the very nice talk. Question in 2D, you could also add some disorder which is breaking time reversal, and then you could get a transition even in 2D. Is that somehow not of interest or not feasible, or?
Well,
I mean, of course, you have to add some, maybe hopping, or I don't know. Well, you have to add some disorder which is breaking time reversal, and then I think you
random magnetic field.
Yeah.
Well, of course you can do it.
Right.
Right.
I mean, that would save you from going into 3D. That's what I mean, because 3D is always more complicated than 2D.
But I like 3D.
Okay, fine. Thank you. I just asked. Then a comment on your, I think on what you mentioned at the end, which came out of the discussion with the referee of one of your papers, is you can also take, for instance, a 2D Lieb, the original 2D Lieb, so the L21, let's say, model, and add which is bipartite, and you can add simply bond disorder only, and then you will destroy, or you get again localization, Anderson localization, but your flatband stays at the same energy, so it's also stays by, you have a macroscopic number of degenerate states at strictly energy zero, and it will still support compact localized states, but they will be different from the ones which you obtain for the ordered case. But they will be still compact. That's quite funny, actually.
That is true, and in fact, that is one of the so okay. So first of all, adding a bit of off-diagonal disorder, hopping disorder, it leaves the energy equals zero states invariant, but I don't think it leaves these states invariant, the one states.
No, probably not, because they are not protected by.
Exactly, they're not protected by chiral symmetry. But so and I told you already, this transfer matrix is much harder to converge. So what we're currently doing is we're adding a sprinkling of hopping disorder in the model, and that allows us to converge the transfer matrix for these particular states. And then we reduce the hopping disorder, and then we're looking at how the phase diagram, the boundaries look like for ever more reduced hopping disorder to estimate what happens at very low hopping disorder. So yes, this is one of the tricks we're currently using, trying to slowly go to the really interesting case of our compactly localized states preserving disorder. Maybe that's one of the things we have to do to get the convergence, not just because it's interesting, like you said, but probably because it's one of the crutches we have to use to get there. But it doesn't really work for those energies out here, and so we'll have to look for a better trick for these guys, for example.
But the funny thing is, if I understand correctly, if you add this disorder only on these, whatever you call them, blue or B or whatever sites, no, in one of these models, then you preserve these compact localized states.
Yep.
Just as they were in the ordered system.
Yeah, exactly. So
right. What I'm trying to say is that if you add disorder in the for the chiral models at least, then you will not preserve the states. They become larger, but stay still compact, if I remember correctly.
Yeah. All I'm really saying is, I mean, it's not very. This is a picture of Warwick, by the way. It really looks like that. Just to draw the energy phase diagram again. Sorry, energy disorder phase diagram. So this is energy, ding, ding, and this is disorder. So roughly, it looks like this. Let's say. And now what we're trying to do is we're trying to do it, and we're plotting it with a little bit of off-diagonal disorder. So basically off-diagonal order is a bit more disorder, so it looks like this. And then we have less off-diagonal order, it looks like this. And if, oh God, and then eventually we're getting closer to the curve that we really want to be at, right? So yes, it changed the nature of these compactly localized states, but allows us to put a sprinkle of disorder in, and hence get better localization, and then hopefully see what is happening. Because at the moment we don't know how this curve looks like, which I'm sort of crossing out. We don't know how the phase diagram looks like for these compactly localized states preserving disorder situations, because it doesn't really properly converge. I mean, we have something, but it looks very, very weird. And maybe I should tell you that it looks like we're getting this behavior where I have this sea of localized states sitting around those flat band energies. Looks like we're getting these localized states, and hence we're getting this. When we cut across here, we're getting sort of something that looks like an inverse Anderson transition. By increasing your disorder, you go from localized to extended. Right? It looks like we're getting sort of something like that, but at the moment, it could just be that's an artifact of the small system sizes that we can reach, and hence we have to do a bit more. We have to come up with better tricks.
Okay, thank you.
Let me stop sharing my screen now.
Maybe what about using, for example, exact diagonalization and maybe level statistics or something like this as an alternative to transfer matrix, just to see the boundaries.
Yes, you could do it, but we've written all the transfer matrix codes. Let's see how far we see how far we can go with this, right? I mean, we have it. If we fail and we never get it to work, then we'll have to do something else. I mean, the diagonalization results for the density of states, which I showed you, tell you we can already do diagonalization. We know the Hamiltons. We could do that as well. But if you want to reach proper system sizes, I mean, you know, then, I mean, the point is, because we have degeneracies, we don't actually want to use sparse matrix diagonalization, which doesn't know how to handle degeneracies very well. So we can only use exact diagonalization, and then we are restricted to very small system sizes. So there's always a trade-off in these numerical codes, right? So at the moment, we've done all this, we've implemented all this, these partial disorders in the transfer matrix, and at the moment we have to gain confidence in our transfer matrix results. And one way to gain confidence is you do transfer matrix with an additional hopping disorder, which doesn't destroy the chiral states at energy 0. See that it works there, then reduce your hopping disorder, and then maybe get another phase diagram and see that it actually works, and get an estimate on how much time it would take to go lower in terms of energy. So, you know, that's where we are. We're very early in that stage. And if we fail with all that, then probably we'll have to do, out of desperation, something like energy statistics, R numbers and all this. Okay, fine, yes.
Okay, do we have any further questions or comments? It seems not. In this case, let us thank Professor Roemer again for his wonderful talk. Hopefully.
Can I ask you something?
Just. Okay.
So this seminar, are you doing it together with the Weizmann sort of, or is it basically the people that used to visit the institute in Korea, they're still participating?
There's no one here from the Weizmann Institute, as far as I can tell.
Sorry, Tel Aviv, right?
Well, yeah, which is a big city, yes. Okay. No, not only. Victor, you're not from Tel Aviv.
Okay, but so it's people that
I'm the only one here from Tel Aviv, and I'm also a member of a study group at Dijon, which we hope to visit once several times per year, but last year we didn't visit because of the...
No, because it's interesting, because we also, our theory seminar that we do in Warwick, we now do together with the people from Cergy in Paris, because having this all online, you might as well do it together, right? So I thought it's interesting to see that you also do that Victor and Amnon are sort of tuning in.
I'm during the week, I'm participating maybe at 5 or 6 different seminars all over the world.
Yes.
All you need is to get into their mailing lists. And
that's an interesting development, right? That's something that we hadn't foreseen.
Very useful.
Well, okay. Thank you very much for your interest. Thank you very much for inviting me.
Thanks, Udo.